We've all seen the science fiction trope where an astronaut travels near light speed for many years to explore distant stars only to return home to find that decades or even centuries have passed since their departure. This would be an example of what scientists call the twin paradox. And it turns out that the twin paradox is actually more than just science fiction. It can happen in real life. But how does it work? Is the passage of time relative? Does this mean we could go back in time? Let's get started. Einstein showed that time was relative, but that doesn't mean time stops. If you were to take two identical twins and send one of them on a high-speed adventure into space while the other stays on Earth, they wouldn't age at the same rate. In fact, the traveling twin would age slower than the twin who stayed on Earth. Here's how it works. Let's imagine a situation where we have a clock that isn't moving. Let's also imagine a person standing next to that clock who is also not moving. Now, let's say that another person starts running past both the clock and the observer. From the observer's point of view, the runner's clock would appear to slow down. The faster the runner moves, the slower their clock would seem to turn relative to the observer. That means if the runner was to pass the observer, their clock would show a time that was less than the observer's own clock. So far, this might sound like it's pure fantasy, but this is actually a real phenomenon that has been observed countless times by physicists. It's called time dilation, and it happens because of the constancy of the speed of light. Einstein taught us that nothing can travel faster than light, and from this principle came some interesting consequences. For example, he showed that mass increases with velocity and that energy and mass are interchangeable. Another consequence of this is that time slows down at higher velocities. And this brings us back to our hypothetical twins. If one twin stays on Earth and the other goes on a joyride through space at near light speed, then time would pass more slowly for the traveling twin. So when the traveling twin returns to Earth, they would be younger than the twin who stayed home. This is the twin paradox. It's worth pointing out that this isn't just a theory. It's something that has been tested over and over again with particle accelerators and satellites like GPS. We know that time dilation works. Okay, so you're saying that one twin goes on a trip and comes back younger than their sibling. That seems kind of crazy. Like, how can someone be younger than their own brother? Well, maybe not as crazy as you think. This is because the difference in age between the twins becomes more significant the closer they get to the speed of light. In order to understand the differences between the twins, we need to first understand some of the basics of special relativity. Remember how I said that the runner E's clock seemed to slow down from the observer E's point of view? Well, that's not just an apparent slowdown. It's a real physical effect. It's as if the runner's clock was actually ticking more slowly. The faster the runner moves, the greater the time dilation effect. As an object approaches the speed of light, its mass also increases. This means that it takes more and more energy to accelerate the object even slightly. As the object gets close to the speed of light, the difference in mass between the moving object and the observer becomes very great. This is known as the relativity of mass. Now let's go back to our twin example. Imagine that the earthbound twin remains stationary and the traveling twin approaches the speed of light. As the traveling twin accelerates, their mass would increase dramatically. Eventually, the traveling twin would be thousands of times more massive than the earthbound twin. At that point, the earthbound twin would be practically massless compared to the traveling twin. According to Einstein's equivalence principle, this means that the earthbound twin would effectively be frozen in time. In other words, time would stop passing for the earthbound twin. That's because the only thing that can travel faster than light is information. And if the traveling twin is effectively frozen in time, then there's no information that can be sent to the earthbound twin. Therefore, the earthbound twin would be unable to receive any information about the traveling twin, meaning that time would have stopped for them. This might seem impossible, but it's actually possible. When particles move close to the speed of light, they really do become incredibly heavy. You might have heard of muons. These are elementary particles that are created in the upper atmosphere when cosmic rays collide with atoms in the atmosphere. Muons are unstable and decay with a half-life of around 2 millionths of a second. That means if a muon was created high in the atmosphere, it would only survive for a few thousand feet before decaying. However, muons have been detected at the surface of the Earth. This is possible because muons can move at nearly the speed of light. Since time slows down at higher velocities, a muon moving at near light speed experiences a much longer half-life than a muon at rest. This means that a muon moving at nearly the speed of light would be able to survive the entire journey from the upper atmosphere to the Earth's surface. So what does all this mean for the twin paradox? Well, it means that it really is possible for one twin to travel into space and come back younger than their sibling. However, it's not as simple as just sending one twin on a joyride through space. In order for the time difference to be significant, the traveling twin would need to approach the speed of light. That's why the twin paradox is often described as a one-way journey. If the traveling twin was to approach the speed of light, then they would experience time slowing down. This means that when they turned around and headed back to Earth, time would be passing normally again. However, from the point of view of the Earthbound twin, time would still be passing as normal. This means that when the traveling twin returned to Earth, they would still be younger than the Earthbound twin. This might seem like a contradiction, but it's not. It's just another example of the strange behavior of time at near light speed. So if the traveling twin could somehow be brought back to the same age as the Earthbound twin, then the traveling twin would be younger. This means that the twin paradox is real. However, it's important to remember that the twin paradox is a one-way journey. If the traveling twin was to turn around and return to Earth, then time would pass normally again. This means that when the traveling twin arrived back on Earth, they would be the same age as the Earthbound twin. It might seem like the twin paradox allows you to travel back in time, but it doesn't. This is because in order to travel back in time, you would need to travel faster than light. Unfortunately, that's not possible. If you want to learn more about special relativity, check out my previous videos. One of the most common misconceptions about the twin paradox is that it's a paradox. It's not. It's just a consequence of Einstein's theory of special relativity. Another common misconception is that the twin paradox is only a theoretical possibility. It's not. It's been observed in experiments with muons and other particles. However, it's never been observed with human beings. This is because it would take an incredible amount of energy to accelerate a human being to near light speed. So don't worry, your trips on commercial airplanes won't be taking you back in time anytime soon. Thanks for watching. If you enjoyed the video, please subscribe and check out my other videos. Special thanks to my patrons for their support.